Imagine you have an assistant, like a brilliant, highly capable assistant who can answer almost any question you throw at them.
Right. Sounds great so far.
Yeah, but there's this massive glaring catch. This assistant has absolutely zero long-term memory for daily routines.
Oh, man. Which completely defeats the purpose of an assistant, right?
Exactly. I mean, every single time you ask them to go get you a cup of coffee, they don't just, walk to the break room. They have to relearn how a door handle works.
Right.
They have to consciously study the operating manual of the coffee machine from scratch, and then they have to mathematically recalculate the exact walking path back to your desk.
Yeah.
Every single time.
That sounds completely exhausting and, well, wildly inefficient.
It would drive you crazy. And think about the last time you asked a large language model to do something slightly complex, like taking raw data and formatting it into a very specific Excel sheet. It often stumbles, right?
Oh, constantly.
It forgets a rule you gave it in the previous prompt, or it gets stuck in a loop of its own errors. And that frustrating scenario is exactly where we are right now with current AI agents. But today, we have a massive shift to talk about. Welcome to the Deep Dive.
It's really great to be here.
Our mission for you today is to unpack a brand new, state-of-the-art research paper that is absolutely foundational to the future of generative AI.
Yeah.
We are looking at a framework called EVSOP,
Yeah.
which stands for Iterative Tool Optimization for Self-Evolving LLM Agents.
It is a dense title, I know, but the implications here are just massive. We are talking about fundamentally changing how AI systems build their own habits.
Right.
Instead of treating every single task like a brand new puzzle to solve from scratch, EVSOP allows an AI agent to actually learn from its own past behavior.
Wow.
It optimizes its workflow and essentially writes its own high-level software to make its life and your life significantly easier.
So to really understand why EVOSOP is such a massive leap forward, we can't just look at what it does. We have to look at the underlying mechanics of why our current systems are failing.
Exactly. We need that context.
Right. So if I ask a top-tier AI agent today to handle a long, complex task, why does it hit a wall?
Well, the bottleneck really comes down to something called atomic actions.
Atomic actions. Okay.
Yeah. If you look at existing agent frameworks, things like React or DFSDT, which basically act as the operating systems for a lot of current AI, they rely on a highly static toolkit.
Wait, let's break those acronyms down real quick so we aren't losing anyone in the jargon. What is React?
Absolutely. So React stands for reasoning and acting. It's a method where the AI essentially thinks out loud, makes a decision, and then takes an action.
Okay, that makes sense. And the other one, DFSDT.
That stands for Depth-First Search Decision Tree.
Got it.
That's a system where the AI maps out a giant tree of possible choices, tries going down one path, and if it fails, it has to backtrack all the way up and try another branch.
Oh, wow. Both of those sound like they require an immense amount of computational thinking.
They do, and it's made so much worse by the tools they are given. Their toolkit is filled with granular, low-level atomic actions.
Like what? What's an example?
We are talking about the most basic computational functions possible. A simple file input or output command, a single-turn web search.
So when you give the AI a complex goal, it only has these tiny, basic puzzle pieces to work with.
Yeah.
It doesn't have like a solve problem button.
Precisely. Because they lack hierarchical efficiency, these agents are forced to orchestrate every single task through fine-grained sequences of low-level logic.
Right.
So if you ask an agent to book a flight and put it on your calendar, it doesn't just do it. It has to think, okay, first I need to invoke the search tool. Then I need to read the raw text result. Then I need to parse that text to extract the date. Then I need to invoke the calendar tool. It just goes on and on.
Which just creates a massive amount of what researchers call reasoning overhead, right?
Yeah, exactly.
Yeah.
The AI is overthinking every single microstep.
And when you have long-term tasks that take 20 or 30 steps, I imagine this leads to a very high risk of cascading errors. Because if step 14 fails, the whole house of cards comes down.
Oh, totally. And the AI often doesn't know how to recover from that.
It's like trying to bake a cake, but instead of just following a recipe that says, mix the batter, you have to consciously calculate the physics of cracking an egg.
Yes.
You have to analyze the chemistry of whisking air into the yolk, and then you have to calculate the thermodynamics of the oven to ensure it bakes properly.
Yeah.
I mean, you would be exhausted before you even got the cake in the pan.
That is a perfect analogy. You are spending all your cognitive energy on the physical mechanics of the tools rather than the actual goal of baking the cake.
Right.
Now, researchers have known this is a problem for a while. There have been recent attempts to fix it. Some newer frameworks allow the AI to dynamically generate brand new Python code to handle tasks as they come up.
Okay, well, that sounds like a good fix, actually. If you don't have the tool, just write the tool.
It sounds good in theory, but here is the critical flaw. These previous frameworks treat tool creation as a one-time event. They generate the code, they drop it in the toolkit, and they just move on.
Wait, they just build a highly specific tool once and never manage it? If you don't manage those tools, wouldn't you just end up with a massively bloated system?
Exactly. The AI creates a tool for finding a cheap flight on a Tuesday.
Okay.
The next day, it creates another completely separate tool for finding a cheap flight on a Wednesday. Over time, redundant, suboptimal tools just accumulate.
Oh, I see.
This creates incredible noise. When the AI is faced with a new task down the line, it looks in its massive toolkit and gets paralyzed by choice. The irony is that giving the AI more tools actually complicates its decision-making and degrades its success rate.
It's like buying a highly specific, single-use kitchen gadget for every single meal you cook, but you refuse to ever throw anything away. Eventually, you can't even find your favorite chef's knife because your drawers are just jammed with useless junk.
Right, you've got an avocado slicer, a mango pitter, a strawberry huller, and you can't even open the drawer anymore.
Exactly.
And that brings us to the core thesis of the EvaSOP paper. A truly self-evolving agent needs more than just the ability to generate tools. It needs a systematic, continuous life cycle to manage them. It has to clean the drawer.
So how does EvaSOG actually do that? How does it organize the chaos?
It synthesizes those tiny, granular atomic actions into high-level, reusable standard operating procedures, or SOPs for short.
SOPs, like the training manuals you get at a corporate job.
Exactly like that. High-level routines that encapsulate complex, multi-step logic. And EvaSOP achieves this through a very specific 4-module lifecycle. Let's dive into the mechanics of the first one. The constructor.
Okay, if I had to guess, based on the name, the constructor is the module actually building these new SOPs. But how does it know what to build? Does it just, guess what might be useful?
No, it's much smarter than that. The constructor acts as a historical observer. It actually parses the JSON logs of the AI's past execution trajectories.
Okay, so it looks at the history.
Exactly. It looks at everything the AI has done previously and hunts for patterns. Specifically, it looks for consecutive tool combinations that are frequently used together to achieve a goal.
So it's looking for habits.
Right. For example, if it notices that every time the AI searches for a user's address, it immediately uses a write file action to save that address to a database, the constructor flags that.
Oh, interesting.
It says, why are we spending reasoning power doing this in 2 separate steps every time? It extracts that logical sequence and physically writes a new Python function that combines them into a single, callable SOP, complete with error handling and semantic schemas.
Okay, I have to push back here for a second. We just talked about the nightmare of the kitchen drawer full of single-use gadgets.
Yeah.
If the constructor is constantly generating new SOPs based on every little pattern it sees in the logs, aren't we bringing ourselves right back to the exact same problem? Doesn't this just create a massive, bloated junk drawer of code?
That is exactly the right question, and it is the exact trap previous researchers fell into. The EvaSOP team anticipated that, which is why the system doesn't stop at the constructor. To prevent that junk drawer dilemma, EvaSOP introduces Module 2, the merger.
The merger. Okay, so this must be the cleanup crew.
It is the structural optimizer. The merger actively scans all the newly generated SOPs and looks for functional overlaps. It analyzes the code to see if 2 tools share a primary objective or use highly similar logic.
Can you give me an example of what that looks like in practice?
Yeah, let me give you a concrete example straight from the paper's experiments. Initially, the constructor generated 2 separate task-specific tools. One was called Order Food Online. The other was called Order Food from Merchant.
Those sound virtually identical. If I'm an AI, I wouldn't know which one to pick.
Right, having both of those in the toolkit would immediately cause that paralysis by choice we talked about. So the merger identified this functional overlap.
What did it do?
It took the underlying code from those 2 narrow tools and synthesized them into one generalized, highly robust tool called Enhanced Managed Food Order.
That's brilliant. It consolidates the capability into one tool that can handle both scenarios.
Exactly.
But I'm curious about the mechanics of that consolidation. Does it just delete the 2 old tools and replace them with the new super tool?
This is where the framework gets really clever. EvaSOP adopts a non-destructive consolidation strategy. When the merger creates that new enhanced tool, it doesn't immediately delete the old ones.
Wait, why not? If the new one is definitively better and less redundant, why keep the clutter around?
Because a larger composite SOP isn't inherently superior just in theory. When you merge code, you might introduce hidden technical defects.
Oh, sure. Bugs.
Exactly. Or it might fail in very specific environmental contexts that the old, simpler tools could handle perfectly. EVASOP doesn't just blindly trust its own theoretical merging. It defers the removal of tools until it actually verifies their performance in a practical setting. Ah, okay. That makes perfect sense. Theory is great, but reality is messy. We need to know if these merged tools actually work outside of a vacuum.
Precisely.
So who is fact-checking this new super tool before it gets permanently added to the AI's brain?
That brings us to EVASOP's rigorous quality control mechanism. Welcome to Module 3, which is the evaluator, and Module 4, the reviewer.
So the evaluator tests it, and the reviewer judges it.
Broadly, yes. The evaluator takes all these newly constructed and merged SOPs and forces the agent to re-execute past tasks. But it doesn't just do this in a hypothetical simulation. It does this in a real-world, stateful environment.
Let's pause on stateful environment for a second. What does that actually mean for you, the listener?
Right, so stateful just means the environment remembers your actions. Actions have permanent consequences.
Like if I delete a file, it's actually gone.
Exactly. If the AI clicks a button to delete an email during a test, that email is actually gone. It changes the state of the inbox. This is critical because the AI has to deal with the real-world fallout of its actions. Got it. So it's essentially a real-world sandbox.
Exactly. The agent is placed in this sandbox and given a choice. It can use its old, slow atomic actions, or it can try invoking the shiny new SOPs to bypass all that multi-step reasoning.
And the evaluator is just watching all of this happen.
Yep. The evaluator meticulously monitors the outcomes, captures new execution logs, and hands that raw data over to Module 4, the reviewer.
And the reviewer gets to be the harsh critic. How does it actually judge the performance? Does it just give it a pass or fail?
It's much more nuanced than that. The reviewer categorizes every single SOP invocation into one of 5 specific states based on how the stateful environment changed.
Okay, what are the states?
Well, the best case scenario is what they call optimal execution.
Which I assume means the tool did exactly what it was supposed to do, 0 errors.
Right. But what if it doesn't go perfectly? The second state is partial utility.
Meaning it works, but not completely.
Yeah. The tool runs, it doesn't crash, but it only achieves a fraction of the intended goal.
Okay, so what happens if the tool runs, doesn't crash, but basically accomplishes absolutely nothing?
The reviewer flags that as the third state, neutrality. The tool ran, compute power was wasted, but the environment didn't change at all.
I feel like we all have some neutrality tools in our own personal workflows, things we do just out of habit that actually achieve nothing.
Oh, we absolutely do. But it can get worse than neutrality. The fourth state is negative interference.
Oh no, that sounds bad.
It is. This is when invoking the tool actually sets the task backward. Maybe it deletes the wrong file or formats a drive it shouldn't have. It actively harms the progress.
Yikes. Okay, and the last one.
Finally, the fifth state is implementation defect.
Let me guess. That's when the AI-written code is just garbage and it flat out crashes.
Exactly. Hard system error. Now, based on these 5 states, across hundreds of test runs, the system performs a global filtering operation. It is an incredibly aggressive pruning process.
Do we know how aggressive?
Yeah, the paper gives us some fascinating data on this in Figure 4, which tracks the lifetime of these synthesized SOPs over several epochs.
And just to clarify, an epoch here isn't like standard machine learning where you just feed in more text data, right?
Correct. In EVOSOP, an epoch is a full life cycle. The system builds new tools, merges them, tests them in the stateful sandbox, grades them, and then decides what lives and what dies.
So what were the actual survival rates? Like, give me some numbers.
Let's look at an SOP called Manage and Send Message. It was synthesized in the very first epoch. It sounded like a great idea, but when it hit the real-world sandbox, it had a terrible 36% success rate. It failed 7 out of 11 times.
Ouch. That's a massive failure rate for something that's supposed to be an optimal routine.
Yeah, the reviewer caught it immediately, and that SOP was aggressively evicted from the toolset. It didn't even survive to Epoch 2.
Wow, gone immediately.
Yep. Then there was another SOP called Retrieve Flight Details. Now, this one wasn't broken. It actually worked, but its marginal utility was extremely low.
So it was just useless.
Basically. The AI almost never encountered a situation where it was necessary, so it didn't justify keeping it in the toolset and adding to the reasoning overhead. After a few epochs, it was pruned as well.
It's ruthless. If you don't pull your weight, you're out of the drawer. But some of them must make the cut, right?
Absolutely. The fundamental SOPs become permanent fixtures. A tool called Fetch Messages for User boasted a 100% success rate across multiple epochs.
Okay, that's what you want to see.
Right. It proved its worth flawlessly and became a core, permanent component of the agent's brain.
So the system is constantly evolving. It builds, it tests, it keeps the strong, and it ruthlessly cuts the weak. I want to zoom out for a second because understanding how it does this leads to an incredibly important concept that the authors call symbolic backpropagation.
Yes. This is perhaps the most profound technical takeaway of the entire paper. To understand symbolic backpropagation, we have to contrast it with standard machine learning.
Okay, let's do it. In standard machine learning, when a model like ChatGPT makes a mistake during training, how does it actually learn?
Well, it uses mathematical backpropagation. It updates its internal weights, the literal calculus and math parameters hidden inside the neural network using something called gradients. You are physically adjusting the dials and knobs of the math to make the model smarter.
Okay, but EvaSOP isn't doing that.
No, not at all. EvaSOP is non-parametric. It doesn't touch the underlying model's math at all. You could plug this framework into a completely locked black box model like GPT-4, and it still works.
Wait, really? How?
Because instead of updating its math, it updates its structure.
Updating its structure. What does that mean practically?
When EvaSOP encounters a reasoning failure, it performs symbolic backpropagation. It looks at the failure, extracts the multi-step logic that caused the failure, and literally rewrites its own procedural software code in Python to prevent that failure from happening again.
Oh, wow.
The code itself acts as the weights being adjusted.
So instead of just trying harder with the same broken process by tweaking a math formula, it essentially tears up the company handbook and writes a better one.
Exactly. It is structural optimization rather than mathematical optimization.
Okay, pruning the junk and rewriting the handbook makes total sense in theory.
Yeah.
But AI is notorious for looking great on paper and completely failing when it hits actual edge cases. When they put this streamlined, self-optimizing brain into a complex scenario, did it actually perform better?
The benchmark data they gathered is incredibly validating. They tested EvaSOP across several domains. Let's look at AceBench Multi-Step, which is a standard test for complex tasks.
Okay.
Using the baseline React framework, just relying on those granular atomic actions, the GPT-4o model achieved an 80.8% success rate.
Which, to be fair, is already quite good.
It is.
Yeah.
But when they wrapped that exact same model in the EvaSOP framework, its success rate jumped to 84.2%.
A solid bump. But I imagine standard benchmarks don't really push the limits of this system.
You're exactly right, which is why the results on a benchmark called Tau2 Bench Telecom are so much more compelling.
Tau2 Bench Telecom. That sounds incredibly specific. Why test it on telecom?
Because telecom troubleshooting is a classic high-entropy scenario.
High entropy, meaning it's highly chaotic, unpredictable, and full of branching variables.
Exactly. It's an environment characterized by a massive tool space and intricate stateful transitions. Think about when you call your internet provider because your Wi-Fi is down.
Oh, the worst.
Right. You have to check the IP address, reset the router, ping the server, verify the subnet mask. It requires tracking exactly what step of troubleshooting you are on.
And if you forget that you already reset the router, you start the whole process over.
Precisely. Standard agents get lost in the weeds here because the reasoning overhead of managing all those atomic actions overwhelms their context window.
Right. They just forget what they were doing 5 steps ago.
But EvaSOP excelled here. It maintained a steady, significant performance lead over all the baseline models, proving that its high-level SOPs can navigate these chaotic scenarios where static tool sets completely fall apart.
I really want a concrete peek under the hood here. We've been talking about these SOPs as high-level Python code, but what does one of these highly evolved tools actually look like? How is the AI actually writing code to save itself?
It's fascinating. The paper provides the raw Python code for one of these SOPs in Appendix E. It's an SOP called Send Message Workflow.
Okay, let's walk through the narrative of this code. If I'm an AI using a standard toolkit and I try to send a message but the user's inbox is full, what usually happens?
In the past, the AI would try to send the message, it would get a memory error, it would panic, and it would likely just stop and ask the user what to do next. It hits a dead end.
But EvaSOP recognized this failure pattern during an earlier epoch. So how did it write the send message workflow to handle it autonomously?
The AI wrote a highly robust 4-step conditional loop in Python. Step 1, the code attempts to execute the basic send message command. If it succeeds, great, it returns a success status.
Right.
But it wrote a try except block so that if it fails, specifically due to a memory issue like a full inbox, it automatically triggers step 2.
Oh, so it catches its own error without bothering the user.
Exactly. In step 2, the SOP calls a completely different subtool to query the inbox database and retrieve the ID of the oldest message currently stored there.
It's finding the oldest message to make room.
Precisely. Step 3, it invokes a deletion tool, passing in that specific ID, to permanently delete that old message and free up space in the stateful environment.
Wow.
And finally, step 4, it loops back and retries sending the original message.
And all of this happens in a single encapsulated function.
A single Python function that the AI wrote for itself. It anticipates the error, manages the environment state to resolve the bottleneck, and completes the primary goal, all without a single prompt from a human.
That is incredible. It went from, I can't send this, human, please help, to, I can't send this, let me clear some space. Okay, now it's sent. And that brings up the core takeaway here, a concept the authors call reasoning compression.
Yes. Reasoning compression is the ultimate goal of either SOP. When you look at the charts in the paper that track the number of reasoning rounds an AI has to take across different epochs, you see this massive, steep drop.
Really? Like a noticeable decline.
Oh, yeah. In the initial phases, the AI is doing a lot of trial and error reasoning. It's struggling. But by the final epochs, after these high-level SOPs are solidified and the junk is pruned, the total number of interaction rounds stabilizes at a significantly lower level than any of the baseline models.
So the AI isn't just succeeding more often, it is literally thinking less to achieve that success.
Exactly. It compressed the reasoning space. And thinking less means saving computational time. It means saving money on compute costs.
Oh, sure.
It massively reduces API latency, and crucially, it prevents the agent from losing focus in those long horizon trajectories. It is the absolute definition of working smarter, not harder.
So as we wrap this up, what does this all mean for you listening right now? Why should you care about EVA SOP, symbolic backpropagation, and reasoning compression?
Well, it changes everything about how we use these tools.
Exactly. The truth is, as we start relying on AI agents more and more in our daily lives, whether it's asking them to book complex travel itineraries, manage our messy emails, or troubleshoot our home network, we aren't going to have the time or patience to hold their hands through every tiny atomic step of the process.
Right. We want them to just do it.
And thanks to frameworks like EvoSOP, we won't have to. These agents are going to quietly build their own optimal habits in the background. They will learn how you work, they will recognize the repetitive bottlenecks, and they will silently write the code to streamline them.
It is the paradigm shift from an assistant who needs constant, exhaustive micromanagement to an assistant who proactively optimizes their own workflow based on pure experience.
Which leaves us with a final, somewhat provocative thought to mull over. We've seen that AI agents are now capable of independently evaluating, merging, and aggressively pruning their own operational logic to become strictly mathematically optimal. What happens when these self-evolving agents are deeply integrated into our corporate structures? Think about your own office. Will these AI systems eventually start looking at human workflows, the very ways we communicate, our endless meetings, our redundant email chains, and identify us as the bloated, inefficient atomic actions that need to be optimized right out of the loop?
It's a fascinating and, well, slightly terrifying question. If the system's singular goal is absolute hierarchical efficiency, human behavior is almost always the biggest bottleneck in the pipeline.
Definitely something to think about the next time you ask an assistant, whether they are human or AI, to go get you a cup of coffee. Let's just hope they don't optimize the coffee break out of existence. Thanks for joining us on this deep dive.